today we are going to be talking about minimum spanning trees. We are going to define what a minimum spanning tree is, and we are also going to look at algorithms for minimum spanning trees. Yeah. So, you all know what a spanning tree is. Does everyone know what a spanning tree in a graph is? Did we define that? Yes, we did, right. So, I give you an undirected graph. Right. So, what is a spanning tree in G? So, spanning tree, the term is composed of two things, tree and spanning, right. So, tree means it should be a tree. What is a tree? A tree is a connected subgraph without any cycles. Connected subgraph without cycles, that is a tree. And what does spanning mean? Spanning means that it should include all vertices. This basically means that it should include all vertices. That would be a spanning tree in the graph, right. So, for an example, if I drew a graph something like that, right, say this were my graph, then I could draw a spanning tree in this graph by, let us say, I am going to use a very, right, let us say I pick this edge in the tree, pick this, pick that, then I pick this and I pick this. How many edges do I need to pick? Is this a spanning tree? No. This vertex is not included yet. So, I could pick one of the edges incidented this to include this. This is a spanning tree, right. So, we know that a spanning tree, if the graph has n vertices, so spanning tree has how many edges? Number of vertices minus 1 edges. Yes. Great. So, now what is a minimum spanning tree? So, a minimum spanning tree is a spanning tree of minimum weight. Sometimes I will use the term weight, sometimes I will use the term length, one and the same thing. right? तो ये वेट और लेंथ कहाँ से आ गया? तो ये यहाँ से आया कि हमें जो है जो ग्राफ है, we are not just given the graph, but we are also given a length function on the edges of the graph. Let me assume the lengths are non-negative reals, right. So, every edge has a length now, every edge has a length, right. So, think of it in the following way, these are certain cities, right, and I can either connect these two cities by a wire, or I can connect these two cities by a wire, or I can connect these two by a wire, or I can connect these. These are the possible options I have of connecting them by wires. Some options are not there. Why? पता नहीं, right? It could be some reason, बीच में पहाड़ आ रहा होगा, ऐसा कुछ होगा कारण, ठीक है. So, this is the graph. Now, to connect two particular cities, I am also told how much length of wire I need. That is my length function, right. So, suppose I told you that you read 3 here and you need 5 here and you need 2 here. What are the units? It could be anything, 1000 kilometers, meters, I do not care, right. So, this could be 1, this could be 7, this could be 4, 6, 9. I just put in some numbers arbitrarily. Yeah. So, we need to connect these cities up, which means we need to create a spanning tree, and I am not interested in any spanning tree, I am interested in a spanning tree for which the length of wire I spend is as small as possible. So that's what I mean by a minimum spanning tree, a spanning tree of minimum length. What is the length of the spanning tree now?
Some of the length of the wires.
So sum of the lengths of the edges in the tree, right? So let's formally define that. The length of the spanning tree equals sum of the lengths of the edges in the tree, right?
Okay, it's time for a homework break. So this is a self-practice homework. You are given a graph with n vertices such that all the edges have length equal to 1. Okay, so all the edges have length equal to 1. Now the question is, what is the minimum spanning tree of this graph? What is the length of the minimum spanning tree of this graph? This is a self-practice homework, so you don't have to submit it. But just for fun, it's a very simple question.
So I might now decide to pick some edges. Suppose I picked, oh, I did not give this a length. I suppose I give this a length 4. Huh? Okay, so suppose I pick this edge, and 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 I pick this edge. ये तो cycle बन गया. So I cannot pick this edge. This is not a tree at all, right? So I cannot pick that edge. So let me pick something else. Let me pick this 6. ठीक है, तो मेरा ट्री क्या है? ये है. What is the length of this tree? 6 plus 4 plus 4 plus 3 plus 5, 22. Right? There might be other trees in this, other spanning trees which are smaller than 22. I am interested in finding the one which is the smallest.
So independent of the root.
There is no notion of a root in the case of spanning tree. When we defined spanning trees or trees in graphs, there was no notion of a root ever. We called also, we used the term free trees for that, right? There is no notion of a root. Right? Since the vertex, since all the vertices are going to be included, you know, अगर आप किसी को root बोलना चाहते हैं तो वो भी vertex include हो जाएगी, तो उससे कोई फर्क नहीं पड़ता. सबके समझ में आ रहा है? क्या ये सबसे छोटा ट्री है इस ग्राफ के अंदर?
3 or 5. If there are more than 2 paths between two cities, choose the path between the smallest weight to the edge.
तो आप ये कह रहे हैं कि ये सबसे छोटा नहीं है. चलिए देखते हैं. Three, 4, 1, 2, 5, 9, 7, 4, 6. Right, and the edges we included were this edge, ठीक है. Now one way you can convince yourself that this is not the smallest possible tree is by saying that, for instance, if I were to include this edge of length 1, then what's going to happen? Will it be a tree? Again, if I will be have a cycle. So that's one property of a spanning tree always. अगर आपके पास कोई spanning tree है, right? ये आपका spanning tree है. Spanning tree मतलब it is a connected subgraph, which means हर एक दो vertices के बीच में एक path है already. अब अगर हम एक edge डाल देते हैं, जैसे कि हमने यहाँ पे एक edge डाल दी, ठीक है, तो अब एक साइकिल बन जाएगी. क्यों? क्योंकि ये जो दो vertices हैं, इनके बीच में ऑलरेडी एक पाथ है ट्री के अंदर. So I can go from, let's say this is vertex u and this is vertex v, I can go from u to v by following the edges of the tree, and then I can take this edge that I added just now back to go to u, which means I form a cycle. If it is a cycle, it's not a tree anymore. Yeah.
Time for a homework break. So consider a graph of which you have selected a spanning tree. Okay, so this is a graph and you picked a spanning tree, and prove that adding an edge to that spanning tree will lead to a cycle in the graph. That's part A. And secondly, once you have formed the cycle, you show that removing any edge of the cycle thus formed will convert it back to a spanning tree. So again, this is a self-practice homework. Just try to formally write the proofs of these two statements. Again, a very simple assignment, and then you can go back to watching your flipped class.
Now in this cycle, suppose the edges have a certain length. मान लीजिए इस एज की लेंथ 3 है, इसकी 2 है, इसकी 1 है और इसकी 4 है. ठीक है. Now what can I do? I can include this edge and drop the edge of length 4. Yes. Will that remain, will that continue to be a tree? If I were to drop this edge, will it remain a tree? Why? Why would it remain connected? No notion of descendant. There is no notion of a descendant.
In a cycle, if you drop any edge, it remains connected.
Why? That's okay.
Because you always have another path.
We have discussed this before,
Yes,
right?
yes.
The point is that if there is a path which gets destroyed, then that path must be using this edge. कब ये जो है कनेक्टेड नहीं होगा? जब दो वर्टिसेस के बीच का जो पाथ था वो खत्म हो गया. इसका मतलब वो पाथ इस एज को यूज कर रहा होगा, क्योंकि हमने यही एज हटाई है एक, तो वो पाथ इस एज को जरूर यूज कर रहा होगा. और अगर वो पाथ इस एज को यूज कर रहा है, तो आई कैन नाउ क्रिएट एन ऑल्टरनेट पाथ बिटवीन दोज टू वर्टिसेस बाय इंस्टेड नाउ गोइंग लाइक दिस बिटवीन दीज टू एंड पॉइंट्स. So that means that there still is a path between those two vertices जिनके बीच में हम क्लेम कर रहे हैं कि पाथ खत्म हो गया. So ऐसा नहीं हो सकता कि कोई भी पाथ खत्म हुआ हो. All paths are still there, or not all paths are still there. All pairs of vertices are still connected. Maybe by different path, but they're still connected. So that's an operation we can do always. I can try to add an edge into this tree, and see if as a result of that operation, so as a result of that operation, I'll clearly form a cycle, right? If from that cycle I can drop an edge of longer length than the edge I added, then I would have reduced the cost of this tree, the cost or the length or the weight. I'll use these terms interchangeably. जैसे for instance, अगर मैंने ये वाली edge add करी, तो I form this cycle. ठीक है. Now I can drop any edge of this cycle and it will still remain a tree. So which is the edge I would like to drop? 4. So I'll drop this edge 4. Okay. And now my new tree has length what? पहले original tree की length 22 थी. तो 22 माइनस कितने से रिडक्शन हुआ है? 3 से. सो इस न्यू ट्री की लेंथ 22 माइनस 3 हो गई. ठीक है, क्योंकि रिडक्शन 3 यूनिट्स से हुआ है. ऐसे आई कैन रिपीट द प्रोसेस. आई कैन सी इफ देयर इज समथिंग एल्स दैट कैन बी डन. Is there something else that can be done? 2
and drop 5.
So suppose I include 2. So now I form this cycle which has edges of length 3 and 5 in it. So it makes sense to drop 5. Right? And the reduction now is 3 units again. So now let me draw the tree we have, because अब यहाँ पे काफ़ी खिचपिच हो गई है. Right? So the tree that I have at this point is This is the tree I have now. This is edge length 1, this is 3, this is 2, this is 4, this is 6. Would it make sense to include some other edge and try and repeat the process? No, because if I include this edge which is of length 4, then this edge is the longest edge on the cycle that gets formed, right? अगर हम ये एज को इंक्लूड करते हैं, मैं यहाँ ड्रॉ नहीं कर रहा हूँ क्योंकि फिर से ये मेसी हो जाएगा, नहीं तो अगर हम इस एज को इंक्लूड करते हैं तो ये साइकिल बनेगी एंड ये द एज आई एम इंक्लूडिंग इज द लॉन्गेस्ट एज ऑन दैट साइकिल. Doesn't make sense to include it therefore. If I include this edge, it's of length 5. The cycle formed may, this is again the longest edge on that cycle. Doesn't make sense to include it. If I include this edge 7, this is the cycle that gets formed and it's 7 is again the longest edge on that cycle. If I include this edge 9, then there is this longest cycle that gets formed. But once again 9 is the longest edge on the cycle. Yeah, and so it does not make sense to include 9 either. So it does not make sense to include any other edge. Yeah, and so actually I should not say and so. The reason is that's not the reason why. So I can't claim from that this is the minimum spanning tree, but it is the minimum spanning tree, and we'll use a different argument for proving that. So this is the minimum spanning tree in this graph. Okay. So MST has length. What is the length of this? 16. Right. So this could be treated as an algorithm for computing the minimum spanning tree. How would it work? You start with some tree, then you try to include an edge, look at the cycle that's formed, see if you can drop an edge of longer length from that cycle. Right? If there is a longer edge on that cycle. If there is, then you can drop that edge, right, and therefore reduce the cost of the tree. So you can keep doing this procedure till you reduce the cost of the tree, and you stop when you can't reduce it anymore. Right? But we will not look at this algorithm, or we will not analyze this algorithm because it will be fairly expensive in terms of running time.
Time for another homework break. Consider this algorithm that Professor Naveen just discussed, that given a graph v comma e with weights on the edges or lengths on the edges, pick a spanning tree. Spanning tree is a subset of edges, and let's say C, T, comma E represents the set of edges in the cycle when E is added to T. When E is added to T, it will form a cycle, and that cycle can be represented by a set of edges, and let that set be E. So the algorithm can be written as following: while there is an edge in E minus T such that the maximum length in C, T, comma E is more than W of E. So the cycle that you form by adding that edge has a maximum length edge which is more than the length of this edge. If that is the case, add E to T and remove the longest edge in CT, comma E. You keep doing this. So the question is, how efficiently can you implement this algorithm? So analyze the running time, come up with an efficient implementation, and see how fast this algorithm you can make it work. Okay, and don't spend more than 5 to 10 minutes on this. Professor Naveen is going to discuss yet another algorithm, and yeah, so you can just give 5 minutes and then go back to your flipped class.
Okay, so we are going to look at a different algorithm for computing the minimum spanning tree, and the algorithm we are going to look at is called Kruskal's algorithm. ठीक है? So we are looking at Kruskal's algorithm for minimum spanning tree. It's actually a very simple algorithm. Let me illustrate it on the same graph that we had before. So I'm going to draw this graph out. Okay. So the algorithm is the following. It says take the minimum edge in the graph. Okay. So this is an example of what's called a greedy algorithm also. You will be greedy. You're all greedy. But we will now be greedy to compute the minimum spanning tree, right? Okay, so what do you think greedy means? Huh? Try to get the largest. Huh? Try to go for less. That's not greedy.
It's the best possible.
At each step, take the best possible choice.
Best possible.
Make the best possible choice at each step,
Not optimum. Best.
right? Without thinking of the future. That's the key thing, right? Make the best choice available. I will not write without thinking of the future, but that's the reason why it's called greedy. You just make the best available choice at each step, right? Now here, of course, our objective is to minimize the length of the tree. So what is the best thing to do at the first step? Take the edge with the smallest length, right? So let's do that. We pick the edge with the smallest length. That's 1. And this gets included into our minimum spanning tree. So I'm now building the minimum spanning tree edge by edge, right? So I've included edge 1, edge of length 1. Now which is the next smallest edge? Or which is the next best choice to make? 2? 2 or 3? Dekho, when you are saying we need to connect it, you are thinking of the future. Don't do that. Think of the, be greedy, as greedy as you can, right? Just take the best choice. Yeah? So the next best is just go for the length 2. Right? Now what does greedy say next? Which is the next edge you will pick? 3. Right? 4. 4 दो एजेस हैं 4. पहले एक लेते हैं फिर दूसरी लेते हैं. चलिए पहले ये वाली ले लेते हैं. कोई भी ले सकते हैं. तो पहले ये वाली ले लेते हैं. कोई भी ले सकते हैं. उसको भी ले सकते थे पहले इसको ले लेते हैं. अब दूसरी वाली लेते हैं. ठीक है. तो अगर हम इस दूसरी एज को लेते हैं so it will form a cycle. ठीक है. Since this forms a cycle, we are not getting what we wanted, right? It's not a tree anymore. अगर मैं ये एज इंक्लूड कर देता हूँ यहाँ पे तो ये ट्री नहीं रहेगा, राइट? तो इसलिए इसमें इस एज को नहीं इंक्लूड करूँगा. बस इतनी रियायत देते हैं, ठीक है? बाकी ग्रीडी.
Greed with intelligence.
हाँ? Right? So you understand the only modification that I am making. If by including an edge, I form a cycle, I don't include that edge. Right? So I am not going to include edge 4. Sorry, edge this particular edge, which is of length 4. Which is the next edge I would like to include? 5. I try to include 5, but 5 also forms a cycle. Yeah? So I don't include 5. Which is the next edge I would like to include? 6. This edge. Right? Actually, I can stop at this point because now I have a spanning tree. Right? Any other edge that I try to include will always form a cycle. Yeah, because this is a spanning tree, and so I can stop. As you can see, this we have already argued is, we have not argued this is the best possible. Actually, there, till now we have not seen an argument for why this is the best possible. Yeah, but this is the same solution we obtained earlier. Soon we are going to argue that this is really the best possible.
Time for the next homework break. So this one is a graded homework. You have to submit it on GradeScope. So we just discussed the Kruskal algorithm to find the minimum spanning tree. So now what you have to do is write a formal pseudocode for the Kruskal's algorithm. Do not look at the solution in the flipped class. You will be graded for not for correctness but for best efforts. So just try to write the pseudocode yourself and then submit it in Gradescope. And once you are done, you can go back to the flipped class.
Does everyone understand the algorithm? Yes? Okay. Can we write down what the algorithm is? Right? So let's just quickly write down what the algorithm is, because it's very easy to write down. So Kruskal's algorithm Okay, so let's say the very first step is sort edges in increasing order of length. Right, and let's say this order is E1, E2, E3, EM. Right, what does this mean? This means E1 is the edge with the smallest length. So to be more specific, L of EI, length of the edge EI, is less than the length of the edge EI plus 1, less than or equal to. Okay, that's what I mean by sort algorithm. Now what should be the next step? For I going from 1 to M, do. What should I do? Take the first element. Take EI to the spanning tree. So we need to define some spanning tree, right? So let's say my spanning tree is T, which is initially null, right? T is a set of edges. So what should I do now? If EI union T has a cycle or is a tree, then T is T union EI. और कुछ कहने की जरूरत है? हाँ? क्या? रिटर्न टी, आई प्लस प्लस फॉर लूप है, आई प्लस प्लस. और कुछ कहने की जरूरत है? नहीं. बहुत कुछ कहने की जरूरत है. हमने you could do that maybe, yeah, पर हमने जो है ये वाली स्टेप में बहुत कुछ छुपा दिया. How do we check?
We can create an array and we can give it give every edge an index, and when it is greater, and we can increase, and when it is greater than 2, then we can, because
edge नहीं vertex.
Wrong. ठीक है, ये ध्यान से देखना पड़ेगा. हाँ? So how do you check if that edge that you are trying to include forms a cycle or not? उसके दोनों एंड पॉइंट्स विजिटेड हैं. What does visited mean? Before including a vertex in the tree, no, we don't include the vertex in the tree. We are only including edges into the tree. As we include an edge in the tree, what does visited array of that edge mean? What does visited array of vertices? ये क्यों गलत है? कोई बता सकता है?
सर एक ही एज से बहुत सारे वो भी हो सकते हैं. एक ही वर्टेक्स में बहुत सारे एजेस हो सकते हैं.
आपने मान लीजिए ये एक एज ली, आप कह रहे हैं एक एज लीजिए और उसके दोनों एंड पॉइंट्स को विजिटेड मार्क कर दीजिए. बहुत बढ़िया, इनको हमने विजिटेड मार्क कर दिया, विजिटेड जो भी हुए उनको क्रॉस कर दिया. ठीक है, फिर एक और एज ली, इसके दोनों एंड पॉइंट्स को क्रॉस मार्क कर दिया. आ गया, चमक गया। ठीक है, अब आपने ये एज ली, आपने कहा इसके तो दोनों एंड पॉइंट्स विजिटेड हैं, इसको हम बाहर फेंक देते हैं। ठीक है, तो ये गलत है इसमें।
So we can do that. We can take both the vertices, the endpoints of that edge, and we can go for DFS or BFS.
DFS or BFS on what?
When you are giving
On the
when
tree.
you're marking it visited, you mark it with component in which it is there. Like suppose whenever you find an edge, if one of its vertices is already visited and the other is not, then the vertex that has not been visited, you mark it in that particular component in which that edge is.
Okay, we'll have to develop this later. ठीक है, we will see how to do it, and the important thing is also to do it efficiently, right? तो ये हमें करना पड़ेगा, इसमें हम बाद में आएंगे। ठीक है, तो एक तो ये काम रहता है कि कैसे हम इस स्टेप को इम्प्लीमेंट करेंगे, बिकॉज दैट विल डिक्टेट द रनिंग टाइम ऑफ दिस प्रोसेस, राइट? बिकॉज एक्सेप्ट फॉर दिस स्टेप देयर इज नथिंग एल्स इन दिस एल्गोरिथम। ये आप एजेस को सॉर्ट कर सकते हैं। हाउ मच टाइम विल दैट टेक? m log n। और फिर बाकी तो ये एक फॉर लूप है, बस यही है सारा जहाँ काम हो रहा है, राइट? सो दिस विल, इफ दिस स्टेप टेक्स लेस देन m log m टाइम over all iterations put together, then this will be an order m log m algorithm. ठीक है? So we have to somehow achieve that, but we'll come to that point later. Before that, we have to argue why this is the minimum spanning tree. ये तो आपने सोचा ही नहीं अभी तक। ठीक है, मैंने कहा, आपने मान लिया कि ये मिनिमम स्पैनिंग ट्री। क्यों है मिनिमम स्पैनिंग ट्री? ऐसा क्यों नहीं हो सकता कि कोई और ट्री इससे छोटा हो? But that means all you're saying is that you cannot greedily improve the tree. Maybe, but there is some other sequence of आपने जो है बहुत सारी और एजेस डाली होती हैं जिसकी वजह से आपकी बहुत सारी एजेस हट जाती, कुछ ऐसे ऐसे होता है।
Maybe possible that if you take each cycle and
Each?
we may prove that MST with the minimum spanning tree must have the property that if we include any edge, the longest edge will not be included in any cycle. The longest edge will not be included in the MST. Then we may prove that this may be unique. This kind of tree is unique.
Okay. No, we are not always taking the minimum, right? We are not always taking the minimum because we are at some times when the minimum forms a cycle, we throw that minimum away.
So it forms a cycle and the other edges are smaller than that.
Right. So
So we are doing it. We are doing the larger. In every cycle, we are discarding the largest. We are discarding it because it forms a cycle and the other edges are smaller.
okay, so we need to formalize this intuition. Right? This is all I'll say is this is not a proof, but this is an intuition for the proof. Right? Let's see what a proof looks like.
Time for a homework break. So this homework is designed for you to begin to write the formal proofs yourself for a problem that you have not seen. So now that you have the algorithm, can you try to formally prove that the Kruskal algorithm will actually find the minimum spanning tree, assuming that all the edges have distinct lengths? So Professor Naveen does talk about the proof in the remaining discussion, but try not to look at the proof and try to give 5 minutes to yourself to try to prove it. And then you can go back to the flipped lecture and see where all you made mistakes in the proof. So this is a very good exercise. Do not look at the solution. First try to do it yourself and then you can check that where you made mistakes.